All right, let me first start by thanking the organizers for inviting me to this meeting on Roman telescope. There's a lot of ringing sound. I think that's people joining Zoom. Okay, we'll let them join the Zoom. Roman is something that I'm pretty excited about, so I'm very grateful to be here to share some potential science cases. As a theorist working on planet formation from the exoplanet side of things, and it's also good to be back in California. So Jennifer already gave a really nice overview of what Roman would be capable of and being able to help the exoplanet science and the exoplanet community. We've already seen a version of this plot. This is yet another version of something that Matt has made a while ago. So I'd like to show this because it really highlights the unique capability of Roman in that in the foreseeable future, at least, it is probably the only mission that can probe the really low mass objects. I'm not just talking about the rocky planets, but all the way down to a couple moon mass objects at intermediate distances, as well as like Neptune size and even rocky planets at wide orbits beyond 10 AU or so. And with that, we can have a better understanding of the shape of the overall mass function of the planets down to the bottom of that mass function. And that is one of the key, really critical key input parameter that goes into making this forward modelings of making a prediction of like what is expected from planet formation theories and how that compare against the measured exoplanet demographics. So why exactly is it that mass function is so important? So let me start from the early stages, the formation perspective. This is purely from thermodynamic calculation of the expected initial gas mass content of a given planet, of a given core mass at different orbital periods. So imagine a core that's embedded in gaseous nebula. And you can already see that it's a very, very steep and sensitive function with respect to the core mass. And on the right, that is the expected measurable size of the planet for a given gas mass content, because it's really the gas mass that controls like how large the planets would appear. And by far, we have the easiest time measuring the size of the planet. So this is what we use to categorize the planets. Are we seeing rocky planets? Are we seeing super Earth, mini Neptune, Neptunes, Saturns, Jupiters? That's primarily driven by the size of the planets. And the reason why this gas mass content is so sensitive to the core mass at a very, very basic level, that's because of the gravitational potential that's given by the core mass. Of course, the heavier the core mass is, the easier it is to hold on to, accrete and hold on to a thicker gaseous envelope. So again, it's the core mass that critically determines the initial gas content of the planet. So that's just formation, but this is also important for the early evolution of the planets once the disk gas dissipates away, one of which is post-formation mass loss, and this is relevant for planets that are quite close to the star. For example, by a highly irradiated planet undergoing photoevaporative mass loss. If you write down the mass loss rate, then not only does it depend on the planet mass, but it also depends very sensitively on the size of the planet. And remember, that is determined by the gas mass content, which in turn is critically determined by the core mass. So again, not just formation, but also post-formation mass loss and the overall cooling process that contracts the planet, that is all determined by the planet mass, and in particular, the core mass. And the way to probe this core mass is to go down to the bottom of the mass function where we're more sensitive to the internal rocky component rather than the thicker gas envelope on top. So with that established, I've mentioned how there are key two observables that I consider would be delivered by Roman. So the first, again, Jennifer already talked about this. The first is wide orbit planets, and the second is the mass function. So right now, what kind of theoretical predictions can we make? So let's start with the wide orbit planets. And This is, we've already seen a version of this plot, mass versus orbital semi-major axis, and there is a blank spot over here right now, which I've mentioned, and Jennifer also mentioned, that would be probed by Roman in a unique way that no other detection methods can probe right now or in the foreseeable future. So theoretically, Alan already mentioned that yesterday, at least in the upper right corner, that could be probed by gravitational instabilities, and Alan is an expert on that, so please discuss with Alan about it. In here, there are this bunch of colored plots, colored points over here. These are sort of theoretically inferred locations and mass of the planets as inferred from substructures that we find in protoplanetary disks. There are red points over here that is labeled as directly imaged protoplanets. You see 4 of them. Be careful with that because except for PDS-70b and C, that are the inner 2 ones, the other 2 are actually refuted by now or highly contested. So really, we only know PDS-70b and C right now because it's very difficult to directly image protoplanets, these young planets at formation as they're embedded in this optically thick environment. Okay, but what are these blue points over here? So you'll see that it's labeled as disks with gaps. When we take a look at protoplanetary disks with ALMA, we've seen a lot of these nearby bright disks with this nice concentric rings. And these rings are considered to come about due to potentially the embedded planets perturbing the disk gas by driving waves. And the dust grains are reacting to that perturbations because that is really the dust thermal emission. So using hydrodynamic simulations, people have been inferring what are the number of planets, where are those planets, what is the mass of the planet so that we can reproduce these measurements. So HO tau is one of the first cases where we found this nice concentric rings, and it can be explained by 3 Saturns at those cross locations. However, depending on what you think the disk is doing or the properties of the disk, very uncertain properties of the disk, the same object can also be explained by a single Neptune at a particular location. It just all depends on the level of diffusive turbulence in the gas, which is highly uncertain because it's very difficult to get a direct measurement of the turbulence in protoplanetary disks, given that it's highly subsonic. It's very different from star-forming environments. So a lot of these blue points over here, just be careful because it comes with a lot of uncertainty. And furthermore, there are certain disks where you may be able to more directly infer the location of the planets, looking at some non-axisymmetric features like velocity kinks. But unfortunately, for a lot of these disks with substructures, if you have multiple ways to infer the location and masses of the planets, they do not line up. So right now, we do not have conclusive and unique evidence of planet for the majority of the structured disks. And again, from a theoretical perspective, one of the key reasons why this is so difficult is because we do not know the disk gas properties, including the level of turbulence. Now, what about the second observable, which is the overall mass function? So this, I believe, is a bit outdated, but like, it most clearly shows that what kind of comparison that people are usually making. So this is a comparison with the ground-based microlensing survey at that time, compared against some population synthesis models of planet formation. And you can already see that depending on how much of knobs you control, you can have very different, somewhat different answers from theories. And again, it all depends on this like very uncertain properties. We don't really know like what are the reliable ranges of the knobs that we can turn. So let me just highlight that by going through some of the key ingredients that go into this PopSynth models. So first, we have to evolve the underlying gas disk, which comes in 2 components. The first is, again, this turbulent diffusive spreading. And again, we do not really know the level of turbulence. We don't know this turbulent viscosity. And there's also mass loss, which can take away angular momentum as well. And that could be photoevaporative, or it could be magnetically generated. once you have this gas disk evolution concurrently, you need to also evolve the solid disk as those solid grains react to the gas evolution. And if you have a smooth disk, the gas parcels are going to move more slowly than the dust grains because of that pressure gradient force. And that's going to cause an inward radial drift of the grains because of the angular momentum transfer from the grains to the gas. If there are some perturbations within the gas due to instabilities or due to embedded planet, then you can have some local the pressure maxima that can trap the dust grains locally as well. Now, all that the main physics though is really aerodynamic drag, and the degree of that drag depends sensitively on this unknown, yet another unknown parameter, which is called the Stokes number. This measures how well coupled the particles are to the gas. It's defined as the aerodynamic stopping time in the units of the local orbital time. And the reason why it is so unknown is because it depends on the gas density, which is really hard to measure, and it also depends on the size distribution of the grains, which is also highly unknown. The exact same physics also controls how quickly and how massive the planet might grow in mass initially, and that is because the exact same physics can aid the gravitational settling of these grains onto an accreting body. Furthermore, once you can and form these planets, then these planets are expected to, as I briefly mentioned, interact with the disk gas and drive off waves, and that perturbed gas will feed back onto the planet, cause a non-zero torque, and that is expected to cause a radial migration of the planet. Now, both the rate and the direction of the migration is also going to be determined by this unknown disk parameters like the viscosity. If you're at low viscosity, low enough such that there's not enough time for the perturbed gas to diffuse away, then you're going to keep on adding to that perturbation as the planet moves. So that's going to reduce or prematurely halt the migration. So this means how massive the planet might appear and where exactly it's going to end up with respect to the star. It's all going to be determined by this very highly unknown parameters like the turbulent viscosity, which we're going to parameterize with the Sakura-Snayev alpha parameter, and the Stokes number. And all these uncertainties really hinder the making a solid predictive model of planet formation that we can use to make a prediction for what kind of planet demographics we would find with the Roman Space Telescope. So what can we do about it? So here's one way to figure out the Stokes and alpha, and that is to go back to these ringed disks. The fact that you see these rings, which you can also see in this radial intensity profile, over a million-year timescale, the ages of the systems tells us that it has likely reached some steady state balance between the aerodynamic drag that's collecting the dust grains at the center of this gas pressure bump versus the diffusive turbulence that's trying to erase away this concentration. This allows us to write down the width of the dust ring, which you can measure, with respect to the width of the gas pressure bump, which is on the order of the gas disk scale height, because that is the characteristic length scale of perturbations within the gas. Which this one you can estimate because we can resolve the location of the rings. And we also know the luminosity of the central object, so we can calculate the irradiation flux and therefore temperature at the location of the rings, which allows us to calculate the gas disk scale height. Corrected for this relative strength between diffusion, turbulent alpha, and drag, the Stokes number. But that's one equation, and we need to solve for two unknowns, two variables. We need one more equation. Now we're going to construct a toy model to come up with the second equation. Another observable measurable from this radial intensity profile of the disk is the integration of the continuum flux, which tells us the total dust mass locked into these rings. We also know separately the initial mass content of these rings when we go look at class 0, 1 disk, so the earlier stages of disk evolution. writing down the radial equation of motion of the dust grains, that is a combination of the dust coupling to the radial motion of the gas and the aerodynamic drag of the grains, we can simply integrate the dust motion back in time to figure out what should have been the corresponding alpha and Stokes so that you can explain the total ring dust mass that got locked at the location of the ring within the system lifetime. So that's yet another equation. We have two equations, two unknowns. We can now solve for Stokes and alpha. And here's the upshot. These are specific to the ringed disk at the location of the rings. It's a local parameter. The upshot is that the Stokes number is very low. It's lower than what is typically used in planet formation models right now. And what that is going to do is it's going to make all that planet formation process very sluggish. We also find that the turbulent alpha is low. It is low enough that if you can form a planet, at least at this wide orbit, minimal level of migration is expected. Now, can you actually form planets? Turns out that's going to be very difficult because you need to first clump up the solid, the grains. And for that, you need to trigger nonlinear instabilities. And for that, you need high enough dust to gas mass ratio. And turns out for these Stokes and alpha, that is not high enough. And the reason for that is because the particles are actually way too well coupled for this level of turbulence. But like, what if somehow you can randomly form a clump that is also bound and stable? Even if you can do that, it's actually going to be very difficult to grow it more than the initial clump mass when you're beyond 10 AU, because again, the Stokes number are very low. So there's minimal level of aerodynamic drag. But if you take all the same disk parameters and push it inside 10 AU, then you can really accelerate the growth of the planet. So what this tells us is that we might expect to find a much more heightened population of planets inside 10 AU than outside, even for the small planets. Okay, so what does this all mean for Roman? So I think this is one way to make that connection between the exoplanet demographics that we'll find with Roman with the disk physics that we can probe with ALMA. So starting with the disk, when we take a look at disk as an overall sample, the disk with those rings, those substructures that I mentioned, those are usually found around massive and large disks. If we take a look at more compact disks, we don't really see that. Now, some of this could be observational bias, but this calculation would tell us that maybe this is physical. For these compact disks, even if there were some inner substructures, perhaps they are having quickly been transformed into planets, so we don't really see those rings anymore. In exoplanet demographics right now, when we take a look at radial velocity surveys and direct imaging surveys, for the gas giants, we already see a significant fall off in their population when you go beyond 10 AU. And what this calculation would tell us in connection to what Roman would give us is that maybe we'll see this fall off even for the smaller planets. So if we can get mass function as a function of orbital distance, this is one way to figure this out. And even if we do not see this fall off, then that's interesting for disk physics because we can use that to figure out what is the formation criteria for the disks that we observe. Okay. Now I would like to talk a bit more detail about some of the detailed features that we might see within this mass functions and see how that might tell us about the formation physics. So the mass function can be interpreted as a fraction of stars that have certain mass at that mass bin of the planets. And theoretically, that can be calculated as the planet formation efficiency times the disk mass function. So the efficiency can be calculated. It depends on the Stokes and alpha, but generally it's pretty low. It's less than 10%. Disk mass function, we already have the data for it. It's pretty bottom heavy, just FYI. And using that, this is the expected initial mass function of the initial protoplanetary systems. You see some curves going pretty steeply while others are not. So that actually could be used as a way to probe the sort of the initial states of this protoplanetary systems. So first of all, if you have large initial seeds, then you don't need as much mass within the disk to grow it up to the target mass. So the fraction of stars having that mass would be higher as compared to starting with the smaller initial seeds. So it's a combination of the required mass content and the fact that the disk mass function is bottom heavy. Perhaps more interestingly, the picture you should have in mind for this is not of a single planet around the star, but actually multiple protocores around a star. And if you have multiple protocores, they can gravitationally interact with each other, drive off orbital instability and mergers. Sometimes you can have scattering as well, depending on the different variance in masses you have, but at least between 1 and 10 AU for these small masses, from direct numerical calculations, n-body calculations, we find that most of them lead to mergers if they have vigorous orbital instability. Now, that merger process can cause a gap in this mass function because you're going to have small planets all merge together, so a pairwise mergers, and it's going to jump up to the next mass bin. And in fact, where exactly the gap might occur can tell you something about the initial spacings of this protocores. If the initial seeds are tightly spaced, then you're going to see this instability at lower masses, as compared to the initial seeds being more widely spaced. It's harder to trigger instability, so you may be able to see this gap at higher masses. So by looking at this more detailed features within the mass function, you may be able to probe the very initial orbital architectural state of these protoplanetary systems. Okay, and finally, I just want to go back to this point about the critical need to have the mass function and how that relates to the gas mass content and the size of the planets. In the exoplanet community, at least right now, I think microlensing often gets an unfair treatment in the community, and that it often gets shafted towards the very last day of the exoplanet conference, and by that time, a lot of people have left. I think it's quite unfortunate. But I'd like to make a science case that actually you may be able to, I think you can make the connection between the statistical measurements that Roman would tell us to more of a deep characterizations that a lot of people are focusing right now with JWST, making this atmospheric characterizations. And let me just go through that argument. So like all these features that you see on the left-hand side, for the lower mass space, the physics that's driving that feature is simply thermodynamics, like how rapidly the gas can cool when the core is still embedded in the gaseous nebula. Now, if the gas mass becomes large enough, when the soft gravity of the gas becomes important, it's no longer thermodynamics, it switches to hydrodynamics. The total mass is now limited by the hydrodynamic flow onto the vicinity of the planet. Whenever you have a switch in physics that's governing the mass, you expect to see some kind of a break in the mass function. And where you see this break will depend on how rapidly these planets initially cool, which you can see has a dependence on the metallicity, which means opacity, which means chemical composition of the planet. So in fact, if the planet accretes more metal-rich substance, it's harder to cool because optical depth goes up. So we expect to find this break at higher masses. And here's a way to demonstrate that. Here, we're making a very simplistic limits as a first pass for dusty envelope versus a dust-free envelope. And you can already see that the expected location of this mass break, we have the best chance to distinguish between this different planet composition at the intermediate distances to which Raman microlensing would be most sensitive. And that is because for the dust-free scenario, it's limited by the molecular opacities, and the internal modes freeze out at colder temperatures. So you're going to have lower opacities farther out from the star. So that means if you can have a precise measure of this break in the planet mass function, we can actually constrain the typical chemical composition of the material that the planet would accrete. Okay, so I'd like to summarize now. So Roman would give us, from exoplanet science, it would give us the wide orbit planets down to very low mass objects, as well as the mass functions. The details of this mass functions could be used as a way to constrain the initial state, like architectural state of planetary systems. The steepness towards the bottom can tell us the initial seed mass. If you can see a gap in the mass function, that might even tell us the initial separations, like how planets were initially organized in their birth state. We can even make a connection between the Roman and ALMA. For example, if you can take a look at mass function in terms of different orbital distance and find a drop in the small planet population inside versus outside 10 AU, then that tells us something about how typical these ring disks are as planet-forming disks. And finally, a precise measure of a break in the mass function will be able to tell us the degree of pollution and the degree of metallicity, at least in a statistical sense, of what kind of composition of the material the planet would have accreted, making that connection between the statistical measurements with the Roman versus that individual deep characterization of the planets that the community has a lot of interest right now with JWST. Thank you.
Thank you, Eve. Do we have any questions online? If not, I'll stand out of the light so I can actually see people in the room. Any questions in the room? Yeah, Dan?
Thanks, Eve, for this wonderful talk. So you talked about the connection between Roman and ALMA and Roman and JWST. I was wondering whether there's a way to also draw a connection between the Roman exoplanet sample and the transiting demographics of exoplanets. And of course, the big question on the composition of sub-Neptunes. Is there some way to make predictions based on the transiting exoplanet demographics of what you might expect to see? With Roman, assuming, some predictions about exoplanet.
Yeah, sure. So I think one way to look at that is like a gradient. So in size, so size function in terms of orbital distance versus mass function in terms of orbital distance, and look at like how different those gradients are. So sort of like dr over dp versus dm over dp. So that I think could tell us about is the final product of the planet. Is it driven by things like opacities and a different chemical composition? In that case, you might find steeper dr over dp versus dm over dp, or is it more heavily dependent on the initial coagulation of the cores? In that case, you might expect to find steeper dm over dp. So I think like that's one way where you can do like sort of a statistical connection between Roman transit, test transit right now, Plato in the future, and the mass functions with Roman.
Any more questions in the room?
So how relevant is the mass fraction function that you more directly get out of McLansing as compared to the actual mass function?
Yeah, so I have to say it's the mass function that is more useful. So if we can have a good like measure of at least like more than half of the Roman sample of what the host star properties are, that would be more useful, because like what we really need is the mass function, and maybe like mass function as a function of the stellar mass.
One quick question.
Eve, can you repeat what you said about the metallicity and the cooling? You said that the higher the pollution or the metallicity, the lower the cooling rate? Is that what you said?
Let me see if I can go back to it.
Or did I mishear that?
Yeah, so if you have a higher metallicity, that means it's more optically fixed. So it's just harder for the radiation to diffuse out. So it's harder to cool, which means that this transition from thermal to hydro, it happens at the higher masses, because you trigger runaway at higher masses.
Okay, let's thank Eve again.